speed of light, the fastest thing known to humans. To be more exact, it travels at 299,792,482 meters per second. Just to give you an idea of how large that number is, light could travel around the diameter of the Earth 7.4 times in 1 second. But how did we come about actually discovering the speed of light, getting it to such a fine number? Well, before, in the past, most people believed that light traveled at an infinite speed. But it wasn't until Galileo's era, or 1616, that this idea was challenged by Galileo. He believed that light traveled at a finite speed, and he set about many experiments to try to determine this, but none of his actually succeeded. Many other people would follow in his path, but it wasn't until 1666, 50 years after Galileo challenged the idea of light traveling at an infinite speed, that the first Danish astronomer would actually discover or come close to discovering light's true speed, and his name was Rømer.
Okay, so who was Rømer, and how did he come about actually discovering an approximation for the speed of light? Well, he was a Danish astronomer, and he would observe the eclipses of Jupiter's moon Io hundreds of times in a year, and he would record all of this data. And around the year 1666 and 1668, he started to notice strange patterns in his data. And that would be that the eclipses, the interval between them, or the time between eclipses, would actually be larger during certain times of year. So I will draw a demonstration and go over a video and show his actual data. So let's start with this diagram here. So this larger circle represents Earth's orbit. This represents the Sun. This right here represents Jupiter, and this right here, this large circle or the small circle, represents Jupiter's moon Io's orbit. So with that information, we will go over what did Rømer actually observe. So let's start with point B, which is right here. Let's call that point B, and let's call this point G. So from this distance between point B and G, he would observe an eclipse at this position, and he would record that. Just so you know, all of this will be exaggerated, just so you guys can understand. This was actually happening at a very, very slight scale, but it was happening consistently enough. Remember, he would record hundreds of data, and this was happening consistently, and he believed that it wasn't because his data was wrong or anything like that. He believed it's because the speed of light was actually finite. So you'll see what I mean here. So let's say he observed an eclipse at position G, and he would record that as May 13th. Let's use that number. So May 13th. And now an eclipse on Jupiter's moon Io happens very frequently. It actually happens 42.5 hours, every 42.5 hours. So he would actually not be able to see another eclipse. Well, actually, he would see another eclipse in another 42.5 hours. So it would do a full rotation, and that would be 42.5 hours, a full rotation, a full orbit. But it wouldn't be exactly 42.5 hours. It would also be some time more, like, let's say, because it has to travel this distance, and let's say that this distance takes light 8 minutes to travel. So he would observe an eclipse at May 13th, but he wouldn't observe the next one until another 42.5 hours plus 8 minutes later. And so he would come about again the Earth would do its orbit, and it would eventually reach position F, where he starts to notice patterns in his data. And remember, this is a course of over 2 years of him recording, so this is just a summary of what he observed. So let's erase this, and let's just take a look at point F to point B. So I'm going to switch the color here, and I'll circle it again from point B to point F. So again, he would record data right here, and let's say that this point was August. I'm going to use Aug for short, August 13th. So he would observe an eclipse on August 13th, and he wouldn't observe the next one until another 42 and a half hours later. But recall that this distance from here to here was 8 minutes. But it would also have to travel an extra distance from point G to point F. So let's say that's another 8 minutes. So it would actually take 8 minutes longer to observe an eclipse at point F than it did at point G. So let's look at point G. So during this time of year, point G's year, an eclipse would happen every 42 and a half hours plus 8 minutes. But during the time of year for F, right here, I'm circling it, it would happen every 42 and a half hours plus 16 minutes. And to be more exact, this is what we have now. So let's see here. Let's go back. So this is Earth. This is Jupiter's moon Io, and that distance that light has to travel is 32.9 light minutes, or 32.9 minutes, to observe an eclipse. But then it would switch during another time of year, so Earth would actually orbit around, as you can see, until it reaches another point at which you can view an eclipse. And at this time of year, since this distance is longer, it would actually be 47.8 light minutes, which is much longer than what it was at the point previously, which was right here. And so to give you the actual data that he had, this is what he recorded in 1676. He would record on June 13th that it would happen at an average 42.45 hours. After 18 orbits, that's the average. So it would take 42.45 hours to observe an eclipse on June. In May, after 31 orbits, he would record that the average is 42.54 hours, and so on, as it keeps repeating, all the way up until the end of August, where the number is 42.63 hours between eclipses. So you can see that this number is actually increasing by around 1/3 of an hour, or 20 minutes longer to observe an eclipse in August, between eclipses in August, than it was in June. So what equation did Rømer actually use for his determination of the speed of light? Well, this was actually lost in a fire that occurred in his area. All science, what he was doing was against a lot of religion at the time, and so when it was discovered he was doing this, all of his work, most of his work, got burned. So everything I explained previously was the few of his work that remained. But it was believed that whatever he was observing would later be known as the Doppler effect, which was discovered by Christian Doppler 166 years later. And why this is? Well, he determined that it takes light 22 minutes to travel from the sun to the earth, which is actually this right here. This will measure C representing the speed of light. So let's go over this whole entire equation to see how he gets this number. So C is the speed of light, or whatever he is trying to find here. P represents the orbital period, or the time for one complete rotation. 2 pi is a whole entire circle. As you recall, pi is 180 degrees, so 2 pi is 360 degrees. T represents the time taken for light to cross the radius of an orbit, so essentially from the sun to the earth. So these two are multiplying. And then we have v, which is Earth's orbital velocity. And if you plug in these numbers, you get what I said earlier, which is 22 minutes for the light to travel from the sun to the earth. And so the exact number that he thought it was, that it traveled, was 214,636 kilometers per second, which is about 20% slower than the actual speed of light. And even though that sounds like a lot, especially since light travels at 299 million meters per second, 20% difference, 20% slower, and such a large number is actually very large. But at the time, you have to keep in mind that this was during the 1600s. So with him only using the data that he observed and some equations that he determined on his own, that is a very accurate number. And a large part of why that was off was because in the 1600s, they believed a lot of things that were false, like how the Earth orbits the sun, for example. Or I meant the sun orbits the Earth and all that. Some stuff was wrong. So Earth's orbit velocity was actually not correct during this time period. The p-value, which is the orbital period, was actually incorrect. And this actually led to what caused his error to be so large, 20% error. But if we take this equation and plug in the real values that we actually know, Earth's true orbital velocity, Earth's true orbital period, we get a number that is deadly accurate to the real number. And this he would create the base of what would later be refined and refined and refined and refined. So this is who created the first, in my opinion, true groundbreaking discovery, the base, the foundation for discovering light's true speed. All over the floor. They watching the way that we